So what are the implications of this new energy and this conditions? So one thing to remember is that we did everything here at constant temperature and volume. So everything we say that applies here applies at constant temperature and volume. The first thing to note is that one nice property of the Helmholtz energy, because it is defined in terms of state functions, U is a state function, T is part of the state of the system, so it's a state function, and S is a state function, is that A is also a state function. So we don't have to think about how the process is happening or anything like that. We can just consider the beginning and the end, and that difference, that change in A, will tell us about what's happening with the system. All right, so this is nice. It's a state function. If we can find, this difference, it doesn't matter. Okay, and then what else do we learn from this? So if we're at constant temperature and volume, if dA is less than 0 for a particular process, we know that it will be favored. It will be spontaneous. And this is true even if we're not considering an isolated system. So for the second law, ds had to be greater than 0. Entropy has to increase for a spontaneous process, and that's true. Basically, we've taken the second law, and now instead of having to look at both the system and the surroundings and calculating different things like that, this lets us look at just one function that lets us determine whether something will be spontaneous, because we took the second law and sort of built it into our derivation here. So if dA is less than 0, our process will be spontaneous. If dA equals 0, we are at equilibrium, or the process is reversible, which is essentially the same thing. A process being reversible just means our system's at equilibrium sort of every step along the way. One way we can sort of visualize this graphically, and we sort of looked at this with entropy as well, is if we have a plot of the Helmholtz energy of our system as a function of time, maybe our system starts with some value up here. Over time, some processes will happen, spontaneous processes, and we'll eventually reach, that should be a straight line, a minimum. So we can think of these as different spontaneous processes that decrease the value of A, and then eventually we reach a minimum value of A, and that occurs when our system is at equilibrium. So what this may be is, maybe we have our system at constant temperature and volume, and there are reactions happening. And the reaction will proceed up to a certain point, and then we reach equilibrium and it stops changing. So the concentrations don't change anymore. And we'll be looking at cases like that later in the semester. All right. So if we know the internal energy change, we can write that delta A is equal to delta U minus T delta S, and that has to be less than or equal to 0. Again, re-emphasizing at constant temperature and constant volume. So this is applicable if we have constant volume processes. Often in chemistry, we are considering constant pressure processes, and so we'll be looking at that in the next few videos. One thing this allows us to do for these constant volume processes is we sort of have an interplay between the change in internal energy of our system and the change in entropy, depending on the temperature, to tell us whether a process will be spontaneous or not. So for example, if we have a process where the internal energy increases, if delta U is positive, could that process be spontaneous? I want you to pause and think about that for a minute. Okay, hopefully you thought about that. If delta U is positive, the process can only be spontaneous if delta S is also positive. And large enough to offset that positive change in internal energy, because we have this balancing act between delta U and delta S. So if delta U is positive, delta S also has to be positive so that this whole term turns negative, and it has to be more negative overall, the T delta S, than delta U. So the larger the temperature is, the more the entropy is going to matter. Smaller temperature is, the less entropy is going to matter. And we'll see a very similar sort of relationship when we get to talking about the Gibbs energy, but it won't be delta U in that case. And so we'll go ahead and stop here. There's one other thing we're going to talk about with the Helmholtz energy, and then we'll get on to the Gibbs energy.